Biology 102, Unit 4, Human Energy Usage and its Impact on the Environment. So in this unit, we're actually going to talk about a topic that's radically different from some of the other topics we've discussed. It's still going to connect to the other material we've discussed because in the process of getting energy to power cars, to power our buildings, to power all of our systems, transportation, communication, every system that's required in order to keep human societies going, we need to get that energy extract it from the earth, extract it from solar energy, extract it from hydroelectric at potential energy out of the flow of water. We need to get it from somewhere, and that often leads to habitat destruction, different forms of landscape use, over-harvesting of resources, these kind of things. So all of that material we've discussed earlier in the course is still going to come up, but this unit we're specifically going to look at different forms of energy usage, exactly how they work. So we're going to look at the science of each one of these different forms of energy utilization and their impact on the environment from where we start in terms of extracting that form of energy to what their overall end usage effect is going to be. So, generating pollutants and things like that. Here is some old archive photograph of some coal miners, and if you are looking carefully at this photograph, you'll notice that the lamps that they are carrying on their heads are actually open flames. So if you imagine going down, hundreds and hundreds, thousands of feet down into the earth, miles into the earth, and the only light that you have is from a candle that is roaring on top of your head, and you are mining coal, and that the dust from the coal is, it's in the air around you. It's flammable dust around you at all times. You can get coal seams on fire all the time. Not only that, but they're carrying dynamite around in order to blast the coal. So very dangerous job, especially since a lot of these shafts that they're building are being held up with lumber that's in a limited supply. So obviously they have to cut down lots and lots of trees in order to get that lumber in order to reinforce the walls of these shafts, and that is not a guarantee. They can still crumble from the blasting or just from geological instability. So very dangerous work, this coal mining. These are kind of classic coal miners. A lot of them ended up getting health complications later in life from black lung or dying in tunnel collapses. But in Pennsylvania in particular, this was a large portion of our economy for many, many years. In fact, the geological period where a lot of coal developed on Earth about 300 million years ago is referred to as the Pennsylvanian period. That's how much coal we used to mine in this area. So one of the forms of energy usage that we are going to discuss is coal. Coal is a fossil fuel, and we'll talk about some other fossil fuels as well. We'll also discuss renewables. For each one of these energy types, we're going to talk about their pros and their cons, and every single one of them will have pros and cons. Now, that doesn't mean that all of their pros and cons are going to be equivalent to each other. I will let you decide which ones have the worst cons and the best pros. Now, energy is, physically speaking, the capacity to do work. And work, from a physics standpoint, is the ability to enact change on a system. So if you can move an object, that is doing work. Pushing something up a hill, say, that is doing work. Or just pushing it across a table, that's doing work. Or if you do a chemical reaction, you change one chemical to another kind of chemical, that is doing work. So all of the metabolism that you do inside your body, that's a form of work. Transporting materials from one side of your cells to from the outside of your cells to the inside of your cells. So the process of digestion and ingestion and getting materials that you need into your body, that's work. So energy is just the thing that you need. It's the motive force that you need in order to be able to get anything done. It's the capacity to do work. But in this course, when we are talking about methods of energy, human energy usage, we're generally talking about the ability to generate electricity as a form of power. So what is electricity specifically? Well, in order to understand electricity, you need to understand the physical material of reality, what matter is made out of. Matter is made, and we're not going to go too deep into chemistry, I assure you. Matter is made out of these little particles called atoms. Here's one. This one happens to be helium, but all atoms kind of look like this. They have three types of particles. They have protons, which have positive charges, and they're in the center. Those are the green ones. They have neutrons, these are the orange ones. They have neutral charges, those also go into the center. And then here's the part we're actually interested in. The electrons go around the outside. Now, the interesting thing about electrons is that they can actually be traded to other atoms. They can move from atom to atom. Protons and the neutrons, they have to stay kind of locked in place, but the electrons, they can be passed around like the atoms are playing hot potato with each other. The electron can go from one to the next, to the next, to the next, to the next. And if you have a whole bunch of atoms lined up right next to each other, like you would in a wire, what can happen is the electrons just keep moving in one direction, next to the next, to the next, to the next, to the next. And here I have a little video that I made up that kind of shows that. You have all of these positively charged clusters, which are the protons and the neutrons, and then the electrons are just being passed from one to the next to the next. You can see that they're just kind of inching their way along. And that flow of electrons in one direction is an electrical current. That's what an electrical current is. This is a direct electrical current. You may have heard it called DC, direct current. Now, if you are familiar with wiring diagrams, this next part is for you. If you're not, you can ignore it because it's only going to serve to confuse you. Wiring diagrams show positive charges moving around a circuit. And the reason is, take a look at this positive gap that's being left behind. As the negative electrons move to the right, there's this gap left over every time they move, and that positive looks like it's moving to the left. And when Ben Franklin was initially discovering this stuff, he had no way of knowing whether it was the positive charges moving in one direction or the negative charges moving in the opposite direction, and he guessed and he got it wrong, and we never updated circuit diagrams. So that's only if you are previously familiar with circuit diagrams, otherwise just don't worry about it. The thing to know is that it's the electrons moving around a wire that creates electric current. Now, the reason I'm showing you that is to lay the groundwork. Anything that we can do that would move electrons around this wire would give us electricity. So, how do we move electrons around a wire? Well, some chemical materials tend to form ions. Some ions have positive charges and some have negative charges. If they have negative charges, they have an excess number of electrons. If they have positive charges, they have a diminished number of electrons. So if you put those two types of compounds together, they will tend to exchange electrons. However, if you keep them separated from each other and connect them with a wire, then the electrons will move through that wire in order to make that connection. They will trade themselves by traveling around that wire. And that's how you can move electricity through that wire. And this is how a battery works. We have a positive side and a negative side. On this slide here, you can see that I've passed the wire through what's called a diode, a light-emitting diode, a LED. And a diode is a device that makes sure that electricity only flows one direction through a wire. So not all diodes are LEDs, but this one does happen to be, and it makes sure that there's only one direction of flow through this wire, and it lights up in the process. Now, if you're a sharp-eyed observer, you'll notice that this electrical circuit diagram shows the charge flowing from the positive side to the negative side, but I told you that electrons are the thing that's actually flowing, and this is, like I said, circuit diagrams show it backward because Benjamin Franklin. Again, that's not something I'm going to ask you on a test. I just want to try to remove confusion when you do see circuit diagrams like this. It is the electrons moving through the wire that is creating electric current, and the electrons are coming from the negative side. Okay, so that's how a battery works, but we don't originally obtain electricity from batteries. We have some sort of like power plant, usually with big turbines that need to be spun in order to get electricity. So, how did those work? Typically, those work through what's called electric induction. Many years ago, some very clever physicists discovered that if you ran an electric current through some wire, through some copper wire, you could make an electromagnet. It would create a magnetic field. And then some possibly even cleverer physicists realized that that might imply that if you spun a coil of copper wire inside of a magnetic field, that, well, since the two are related, that might produce electricity. And it turns out that that is in fact true. If you spin a coil of copper wire inside of a strong magnetic field, you can produce electricity. And here I have a desktop induction motor that I've set up, and that's all it is. It's a coil of copper wire with some neodymium magnets that I set up, and I've rigged the positive and negative leads here to a light emitting diode, just a little green LED. So there's no battery attached to this, there's no alternate power source or anything like that. It's just the magnet and the copper wire. Now, if I spin this really hard, I get a little bit of a charge going to that LED, a little bit of a light. But I wanted a nice, strong demonstration of what you can do if you really start spinning this thing fast. So what I did was I hooked up my power drill to it. What I want to make clear, though, is that there's no electric charge coming from the power drill to this device. I'm just using the mechanical motion of the spinning in order to impart motion to this. So let's take a look at what that looks like. So there you can see the LED is lighting up, and the only thing connecting the power drill to this device is this rubber band that is hooked up to the wheel here that's causing it to spin. So, what does this tell us? If we have a setup like this, coil of wire in a magnetic field that can be spun, any kind of mechanical motion that can spin this can be used to generate electricity. This is the very basic way that most of our electricity is produced. This is the way that windmills produce electricity. That's why we want those windmill blades to be spinning. This is how they generate electricity. This is how hydroelectric plants generate electricity. This is how coal-fired power plants generate electricity. This is how nuclear power plants generate electricity. All of it, at some level, comes down to spinning a turbine. The exceptions to this would be solar. Solar works on a different principle. Hydrogen fuel cells, to some degree, work on a different principle. That's more of an energy storage solution than it is an energy generation solution. And certain types of home heating and cooling work on different principles as well. But in terms of electricity generation, except with solar taken into account, most of it comes from this form of induction, spinning wires inside a magnetic field. So if you understand that, you will understand most of what we're going to cover pretty soon. And then it's just details about how each different form of energy production approaches spinning these wires. So here's a question for you. How many different methods of getting energy can you think of? I've already mentioned some, but there's more. There's lots of different ways we could get energy. So go ahead and just write a few down. Go ahead and pause the video and write a few down. There's some follow-up questions though. Can you name any drawbacks, any benefits and drawbacks for each type of energy? There might be some that you can immediately think of what the drawbacks are because you've heard about them a lot. But some of you might have some preferred energy types. Does anyone have a strong preference for one or a few kinds of energy over others? Can you think of the drawbacks for your preferred energy types? Can you think of benefits for some of the energy types that maybe you're not so fond of? And as I said before, there are pros and cons for every one of these energy types. So go ahead and take a pause and see if you can just brainstorm a few. All right, keep those in mind, and then we're going to go through all these different forms of energy. So the first question is, what are the most popular forms of energy, or I suppose not popular, what are the most common forms of energy in the world? We can broadly group these by renewable energy sources and non-renewable energy sources. We've talked about renewable and non-renewable resources before, so real quick, a non-renewable resource is one that it really doesn't matter how slowly we use it, eventually it will be used up because it is a finite resource and it doesn't come back over time. So on this chart you can clearly see oil, coal, natural gas, and nuclear. All of these are non-renewable resources. Coal, oil, natural gas, those are fossil fuels. They were formed 300 million years ago. That's too long of a period of time to form to be considered renewable on any kind of human time scale. So as far as human societies are concerned, we're never getting any more of those things. We have used up the majority of those resources already, and they will disappear at some point. Nuclear, similarly, all of the heavy elements, uranium and thorium and everything else that we could conceivably use in a nuclear power plant, those elements are formed in the supernovae of stars when they explode, and therefore we are never getting any more of them than currently exists on Earth, so it is also a non-renewable resource. Renewable resources are those that if you use them at a sustainable rate, you could essentially use them indefinitely because they come back. Whatever the thing you're getting energy from, it will renew itself. It'll come back. So because it comes from biomass, or because it comes from some sort of biological or geological process, or it's wind or water or solar, something like that, there will always be more of it over time. Worldwide, about 9% of energy comes from renewable resources and about 91% from non-renewable resources. Overwhelmingly, oil being the biggest chunk out of this pie chart, with coal being a close second. In the United States, it's 5% renewables, with again, oil being the largest chunk of the pie chart, but with natural gas actually being the second largest chunk. Coal actually has shrunk quite a bit in the United States, and the majority of the decrease from the coal industry in the United States is actually not due to the growth of the renewable market. The renewable market has grown in the United States, don't get me wrong, but it's actually because of the growth of the natural gas market. We've been burning more natural gas and therefore less coal. And the reason why we've been burning more natural gas is because of technologies like fracking. So that is essentially why the coal industry is decreasing and coal jobs are fewer in the United States. You can also see that we get a lot more of our energy from nuclear power than the rest of the world does, comparatively speaking. Still not an enormous amount, but we get more of our energy from nuclear power than we do from renewables, at least when this chart was made. I believe this is less than 5 years old, though, so it should be pretty close. On this chart, you can see U.S. electricity generation by major energy source from the 1950s up to 2018. So this terminates about 4 years ago. This is pretty recent data. And you can see that coal was our major energy source in the 1950s. And then all of these our total energy consumption increases massively over time. You can see that we're just burning more and more and more energy. We need more power in order to sustain our lifestyles. And you can see that nuclear energy starts showing up. We don't start making nuclear power plants till a little bit later in the game, but then they grow pretty substantially. And right here, you can see the growth of natural gas starting to take over the pie slice that would have been coal. So you can see the depletion of the coal industry and natural gas kind of taking that over. You can also see that renewables have been growing in the past few years. Right towards the end of this, they're getting a larger and larger pie slice here. And petroleum seems like it's been kind of thinning out, but it's always been a relatively small amount, at least for electricity production. Petroleum has always been better for transportation, for burning in gas tanks and for boats and other types of transportation methodology. Petroleum is really good for combustion. Other kinds of energy are really good for electricity production. So to expand on that last point, that some energy sources are better for some purposes than they are for other purposes, take a look at this chart. So coal is really good for electricity production, and it's not so great for transportation. It hasn't been a good transportation. You might notice that we stopped creating like coal-powered steamboats and trains, and we also don't just shovel coal into space heating anymore. There are other systems that are more efficient for that. Oil is really good for transportation, and it's really good for it's okay at space heating. We have when I moved into my house, we had an oil burning furnace, and depending on the source, it can be good for electricity production, but it's pretty expensive, oil, and so we don't generally just burn oil for like massive power plants. If you look at this entire transportation column, you'll notice that oil is the only one that has high efficiency or high yield on the transportation one. So if that's the only one that's really good for transportation, we're going to want to center that on transportation and use all these other methods for electricity. Natural gas is really good for electricity. It's pretty good for space heating. We get a lot of natural gas houses. That's a common method of heating houses. That was not an option on my street. There's no natural gas line going to my neighborhood. And there are some actual natural gas cards. There are certain countries that have like natural gas pumps, just like you would go and get gasoline. It's liquefied natural gas you can pump into your gas tank. Geothermal, real good for space heating and electricity, or I should medium it has here. These are different forms of geothermal, though. We'll talk about both of them. The electricity generation can only be done in areas that are geothermally active, and by that I mean they would be like locations where you get hot springs, geysers, where you see steam kind of raising up out of the ground. And space heating can be done just about anywhere. My house now has a geothermal heating and cooling system. Our old oil system broke within a couple years of us having moved in here, and we had to choose, because there's no natural gas option, whether we were going to get a new oil system or pay a little bit of extra money and get the geothermal system, but then never have to pay for the oil delivery again. And it was both ecologically and economically a better decision for us to go for the geothermal system. So that's what we ended up going with, and it has been fantastic ever since. Now, a lot of these other options, they're not great for space heating, passive solar being the exception. because they're just for electricity production. So while they can be used for heating by powering an electric heater, they can't like wind power can't be directly applied to heating in the same way that burning natural gas can be directly applied to heating. You would need to get the electricity and then use that electricity to power an electric heater. Passive solar is a little bit different because that has to do with building windows that are really good at letting light in, but also trap the heat inside. So well-insulated, transparent windows that are facing south, for example. And that's why that is a very efficient means of heating your house. So since each energy type has certain best applications, they're going to be used by different sectors in different ways. So 72% of petroleum is used by transportation. And you can see here that they've actually figured out the percentages on both sides. So 72% of the petroleum supply goes to transportation, which meets 92% of their energy requirements. The rest goes to industrial practices, the other 23%, and then a very small amount, 5%, goes to residential and commercial needs, and then 1% to electrical power. Meanwhile, nuclear electric power, 100% goes to the electric power industry here. Coal, you can see 91% of coal goes to electric power. I'm just going to talk about the biggest pie slices here, the biggest chunks. Renewable energy, 57% goes to electric power. And same with natural gas, 34% goes to... Actually, this one's actually pretty well split. So natural gas, 34% goes to electric power, 35% goes to industry, and 28% goes to residential and commercial because it's really good for space heating as well. So natural gas is probably the most evenly split between these industries. And like I said, a very small amount actually goes to transportation because there are cars that run on natural gas. You just don't really see them in the United States. Now here we're grouping all renewables together. I promise we will talk about them individually.